Let me go ahead and check that though. All right, go back to Twitch. Let's hope it's okay. All right, I think things are good now. I don't know what happens there. Every now and then when I like open up Twitch, maybe I'm not too sure exactly why it does that. Let's see if I can pop out the chat. Can you guys hear me now? I saw Larry's comment earlier. I'm not too sure if you guys can hear me. All right, perfect. Give me 1 second. I'm about to just go quickly grab something and then I'll be right back. Just give me 1 second. Oh, you're out here. Okay. And I'm back. All right. So, today's problem I've kind of put together, and yeah, we're going to see how it works out. All right, so I'm going to kick it off like this. I have very mixed feelings about going to the hospital, right? Unless I'm going there for like a routine visit, I typically don't like to go. Well, I see that one person agrees with me here. Unless I have to go like for a routine visit, I don't like to go to the hospital. But typically, whenever I do go for like routine visits, just being there and listening to the doctors talk about various things, it's interesting, right? And so I recall one time I went to the hospital and some imaging had to be done. And of course, they have a bunch of various different type of imaging devices to use. And of course, those devices will be used depending on whatever the situation is. Well, like for example, when my wife was having our children, she had to go in for regular ultrasounds. And whenever you're thinking about how an ultrasound works, oh no, I'm sorry to hear that, Guido. Hopefully things get better as the stream like moves on. But ultrasounds, and given my background and what I've learned, I'm like, oh, okay, I can see how an ultrasound works, right? You're gonna pump a sound into some region. That sound's gonna bounce around and interact with whatever is in that region. It's gonna come back to your detector, and your detector turns that information into an image, right? And of course, the sound that's being pumped into the region is going to be dependent upon the temperature and density of that region, right? And you're basically looking at the amount of time it takes for the sound to get back, as well as how much of the sound has been absorbed. And so I'm thinking to myself, like, okay, that makes sense to me. I get how this particular imaging device works. Then we can move on to another imaging device, like the X-ray machine, right? You basically, you have a device that creates X-rays. These X-rays pass through some target onto and below the target, of course, is going to be the actual detector, and the amount of X-rays that actually gets through to the detector lets you get your image, right? Okay, I get that. But then there was another device, the MRI, which kind of brings us to the topic of today's discussion. The MRI, I had no idea of how an MRI works. I just know that the M in there stands for magnetic. And I know the rest of the magnetic resonance, I think, MRI, imaging device, something like that. But I had no idea exactly how was it using magnetic fields to get an image, right? And so today, probably like about for the past like 30 minutes, I've been trying to learn exactly how an MRI does what it does. And so I'm going to turn that into a problem eventually, but right now we're going to talk about the MRI. Wait, Larry states, oh yeah, me too. It's been 28 months to the last since the last time. 28 months since the last time. You're talking about like regular visits to the doctor. Oh, I'm well overdue for a regular visit to the doctor. All right. So we're talking about MRIs. Let's go ahead and let's look at what an MRI machine looks like. So MRI machine. See if we can get some images. Oh yeah, note guys. So today's discussion, most of it's going to be driven by images we're going to find online. Okay, these look good. Let's take one with people in it. Okay, note that these are not my images, and I'm just looking at images on Google right now. But you see here that we have a doctor in our image, or a technician, and we have our patient laying on this bed, and of course this big like what looks to be like a cylindrical or extended donut looking shape in the background here must be our MRI machine. And so my idea here is that within the machine, we are producing magnetic field lines that have a specific orientation. That is, we're not getting random magnetic field lines. We're getting more or less constant, constant direction magnetic field lines, and they're going to pass through our target, in this case, our patient, and then information is going to come from our patient, of course, to produce an image, and that's what we're going to get into today. Exactly what that information is and how that information was generated. Let's look at some comments here. Oh no. Emergency. See, those are one of those times I don't like to go to the hospital. I mean, it's needed, of course. Especially the emergency room is pretty serious. But I like to keep those visits to a minimum if possible. Not to say that I have much control over that, but I mean, if possible, to keep it at a minimum. All right. So, we have our MRI machine. It produces magnetic fields, and then from there, those field lines are going through our patient, and then we're getting an image out of this. All right, so exactly how are we getting this image? What's going on? Basically, how is the magnetic fields that are being produced by our MRI machine allowing us to take these images? All right, so I've always wondered. Okay, guys, excuse my ignorance. So first off, hello, skeptic Psy. I've always wondered what does that mean exactly? Does that mean like you're agreeing with the person above you, or you had a similar situation happen to yourself? I've never known what that means. I'm gonna go ahead and continue, and if one of you guys can answer, what does that mean? What skeptic side put there? It'd be much appreciated. All right. So what's happening essentially is that the magnetic field lines are causing the in this case we're gonna take the hydrogen atom, a free hydrogen atom within the human body. It's causing those hydrogen. Well, in particular, it can cause a hydrogen atom or any other nuclei to undergo some sort of alignment. So if we take specifically hydrogen atoms, so let's see, magnetic field, and we're going to use the hydrogen nuclei, which is the proton. Magnetic field and proton. Let's see. Images. Let's see what's going on. Let's see what we got here. I want to find a good image. Oh, wait. Proton alignment. Okay, this looks good. I like this one. Or even this one, actually, I think. But let's go with this one, right? So within the human body, of course, if you have these free hydrogen atoms like moving around, or hydrogen nuclei or protons moving around in the human body, they start off with the situation of being of what we're seeing on the left hand side of the image. That is, there is no field, and there's a bunch of different. I mean, they're all spinning, of course. They all have their own intrinsic spin. But as far as the red arrows are concerned, whether the spin is considered to be up or spin is considered to be down or any other direction, it's random, right? And that's kind of what we're seeing here on the left-hand side of the image. We have our protons, they are all spinning around, and their spins, though, are all in random directions. But the moment you introduce this external field, external magnetic field, you kind of end up getting these alignments where the alignments themselves are going to be either parallel or anti-parallel to the field that's passing through that region. What's up, Uncle Bill Druin? Yes, nuclear does not mean radioactive. Yes, good point. But hey, Uncle Bill Druin, we're talking about the MRI and how it works. All right, so yeah, so the MRI machine, it pumps this magnetic field through our patient, a uniform magnetic field, or the terminology I ran across was static, and I think that more so means the direction of the field. The direction of the field is going to be in a constant direction, and we basically get this alignment. And so now that we have this alignment, the key thing to note here is that for the protons themselves, something special is going on. So let me pull up another tab. Let's make sure that you guys can, of course, see everything I'm seeing here. Perfect. And so, how can I put this exactly? So I want to be able to state energy level proton magnetic field. This works. But I want something that's a little bit more descriptive to help us out here. Here, we'll use this one. All right. So, as far as our protons are concerned, when there's no field around, they're basically just going to have, their one single energy level. However, when there is a magnetic field present and they're within that external field, they now have this ability to be in one of two states. And these one of two states correspond to the spin in which they have while within the magnetic field. And so what we're seeing here is on the left-hand side, and of course I'm going to start from left to right. On the far left-hand side of our image, we have this upward pointing arrow with energy next to it, basically indicating that the magnitude of the energy increases as you go up in the image. These double bar lines that we're having here, after that line there, the upward arrow line, corresponds to the situation of where we just have our one energy level for our proton when it's not in the presence of an external field. Therefore, B sub 0 equals 0. Or B not equals 0. However, in the situation of where now a field's present, that energy level kind of splits. And it splits into one of two scenarios where the top line, I don't know if you guys can see my arrow, I mean my pointer, but the top line here corresponds to the situation of where the proton has a downward spin and m equals 1/2. I think that's the that must be one of the quantum numbers actually. It has a half integer spin of 1/2, positive 1/2. All right, if I'm understanding that correctly. I know m is the quantum number, but I'm kind of confused now between the fact that it has a downspin. Well, a positive 1/2 integer spin. Cool. I'm gonna have to beef up on some of my quantum mechanics here. But with the bottom line situation, the proton spin it would have an up spin. That's what this arrow here indicates. And that would correspond to an m value of negative 1/2. And of course, this is now in the presence of an external field. Therefore, B naught does not equal 0. But the key thing is that there's going to be a change in energy, or there's going to be an energy difference between these two energy states. That's equivalent to 2 times mu sub z, which is going to be the magnetic moment of whatever particle you're talking about. That's what the z I'm assuming stands for whatever nuclei you're talking about, atomic number z. In this case, we're going to be talking about a proton, so u sub, I guess, 1 would be what we apply here. And this is going to be multiplied times the strength of the magnetic field. And so this will end up giving us what the change in energy is between these two states. Gotcha. Thank you, Skeptic Sai, for explaining that to me. All right. Hopefully, so far we're good so far. So basically, you put your patient into the MRI machine. The MRI machine produces this static magnetic field that now passes through our patient, causing an alignment of all the, in this case, we could say protons, but really it can apply, I guess, to any nuclei. But alignment of free protons within our patient, and now we're going to basically get a separation of some of the protons having an up spin and some of the protons having a down spin, where the energy difference between these two particular states is given by this formula here. Delta E is equal to 2 times mu sub z, or in this case the magnetic moment of a proton times its times the strength of the external field. All right. So to kind of move on from here, and how did I want to move on from here? So we have the difference in energy, right? So the next thing to note, of course, is that, and again, I told you guys earlier that most of the discussion today will be driven by images, right? So those two energy states, of course, are given by that formula I just showed you. 2 times mu sub z times b naught. But that change in energy also has another relationship, especially when you're talking about energy states of like atoms and stuff like that. That change in energy is also related to like photons, right? Or transitions that occur within atoms. In this case, though, it's not an electron transition, but it's basically energy that can be given to, let's say, a proton that's in the lowest energy state, which is going to correspond to the spin up state. We can give energy to that proton by hitting it with a photon that has the same energy difference that corresponds to 2 times mu sub z times b naught. And the equation we want to use, of course, so energy of photon. I know the equation, but I want us to be able to actually see the equation as well. Here we go. Typically, this equation you think of as using it for when you hit an electron with a photon and it bounces up in an energy level. But the same concept can be used here with the proton. So I'll just go ahead and we'll just use this one right here. Even though it says E, think of that as delta E is equal to h nu, where E is going to be the energy of our photon, h is Planck's constant, and then nu, or frequency f, is the frequency of our photon. So we now kind of have a relationship now here between the frequency of a photon that would hit a proton in an upspin state that's within an external field, and how if that energy of the photon is equal to delta E for the last equation I just showed you, this equation here, we can now essentially change the spin state of the proton. Oh, I'm sorry. Okay, guys, let me know what's going on. I'm seeing Larry's comments. Protonium. Okay, what is that? I honestly don't know what protonium is. The specific name of hydrogen 1 as opposed to... Oh, that's what it is. Okay. Yeah, if I'm not mistaken, deuterium, isn't that a proton, but that also has a neutron as well? And I've heard tritium before, or tritium, or I think it's tritium. I don't know. I'm not too sure, but I don't really know what it's Okay, that's what it is. Okay, perfect. I'm gonna assume that tritium is gonna basically just be a proton, but it has 2 neutrons. I don't know this though. I'm assuming this. I would have to look it up. But going back, but I want to make sure that this is that everyone's understanding what's going on here. If anyone's not understanding, let me know, and I'll try to make the correction. All right. So I'm actually now going to like put this stuff together into like one coherent equation. Right. So what we're going to do now, because I'm trying to set up a problem here too as well. We are going to switch scenes. But let me set something up really quickly, actually. Let's use tech for this. And I guess the problem I want to set up is if we are like first year, lab techs. We haven't even graduated yet. We're still in the learning process, and we're basically going to be given a scenario of how we need to like use this MRI machine, including the math that we've now just learned, to like figure out some stuff. So let's see. Desktop. I need to go here. Astro office hours. I need to add another folder to my Astro office hours directory. All right. To include today's problem. All right. I think that's good. Set up this quick template. So you guys can actually see what I'm doing. I'm going to put that in as well. Let's just do this one. This will now become our tech window, which I'm going to move down here. Don't worry, guys. I'm going to fill in the blank space. Oh, there goes my dog. He wants attention. We'll have to probably wait a little bit. Cody, 1 minute. Yeah. And we can get rid of that one. And in general, this is going to be physics, right? This isn't really astronomy, so. Physics. I'm just going to put MRI for here, for now. All right. We can typeset this. Physics, MRI. Sorry, guys. Give me 1 second while I set this up. I'm nearly done. And we can move on. And save. What's going on? See if that makes a difference. Okay, for some good reason, it's giving me... Oh, there we go. All right, sorry, guys. Here we go. Let me now add this, and then we can move on. Where is it? PDF. All right. Quick check of comments. Yeah, Cody. I guess Cody felt like he needed to jump in on the fun here. All right. So let's go ahead now. I mean, go ahead and put together the information that we have so far, and being able to relate. So no indent. I have no idea what to call this actually. I'm just gonna put equation. I'll come up with better wording for it in a minute, but all right. But this is actually quite fun learning about this though, because I've always kind of wondered exactly how does an MRI work? What is it doing? And so I know now that the change in energy between the aligned spin states of a proton when in the presence of an external field can be related to a photon that can bounce it. Well, a photon that can either bounce it to the higher energy spin state, or upon de-excitation can emit a photon when going back down to the lower energy spin state. And again, I mean, this has to happen while there's an external field. Without the field, you don't get these two these splitting of the spin states. All right, this is gonna have to be, let's put it as delta E is going to be equal to, and I think that was a 2 times a mu. In this case, we're talking about free protons in the human body, so I'll put mu sub p times some external field, which in this case, I'm just going to put it as B total. Because it turns out that you can also get, if you have let's say not free protons, but if you have protons that are part of a molecule, your total field is going to be made up of contributions from the external field that's being produced by your MRI, as well as fields that you're going to end up getting from other electrons and other charged particles that are in the vicinity of your bound, let's say for lack of better words, your bound hydrogen atom. So I'm just going to put this B total. In this case, we're saying B total is completely the external field being produced by the MRI machine. And that this is going to also be equal to H. I'll put nu, but H nu is the same thing as the nu is the frequency of the photon. So this is the equation we have to work with, right? And I believe in a nutshell, I mean, that's pretty much exactly just how this MRI is working. Oh, wait, no, there's one more thing I'm forgetting here, actually. So the MRI, of course, is producing the static magnetic field that's passing through our patient, aligning the protons in such a way that either they're going to be in a spin up state or a spin down state. Now, the other key thing here is that the MRI machine is now going to pump radiation. It's already, making sure that the static magnetic field is passing through our patient, but now it's going to illuminate, I guess, our patient with photons that have a frequency that is equivalent to the change in energy between the two spin states. And so what this ends up doing, though, and if we go back to our image, so let's go back to the previous scene. I think that was, yes. If we go back to this, what this does now is it forces all of these protons to now be at the highest energy level state, which is going to correspond to the spin down state. So now everything's at the same state now because it's pulsing these photons into the patient. And so upon de-excitation, of course, now we're going to end up getting photons back out, and it's going to be photons back out from all of the protons that are in this state, of course. Let me go to the comments here. Is a brain scan an MRI or a CAT scan or a CT scan? Well, if I'm remembering this correctly, I think a CT scan or a CAT scan uses X-rays, and so I don't know if you'd wanna pump X-rays into someone's brain. So I'm not. Unfortunately, in this situation, I'm not that type of doctor. So, but I would think, just given of my very limited knowledge of CT scans. In fact, let's look that up actually to make sure I'm right on what I'm saying about a CAT scan. But I think CAT scans are X-rays, and I don't think you'd want to pump X-rays. Well, take that back. Of course, you'd want to probably image the skull. But I'm seeing here, though, just off to the side, though. I mean, I guess you could pump X-rays into the head. But yeah, I mean, I was pretty sure that I think the CAT scan are X-rays. So maybe you can do both of them actually. I don't see any reason why you couldn't do an MRI of a person's head. Because from what I was seeing online, with the MRIs, it's all radio frequency. I was just kind of concerned about the fact of pumping X-rays into the person's head, but these images here clearly show images of the head, and I guess these are all supposed to be related to CT scans. But maybe the things that you can see with the CAT scan versus the MRI are different. Let's see the questions here. So yeah, thank you, Tom Van Scott, and welcome to today's stream. They did, okay. 3 times in 2 hours. Oh, God. I'm sorry to hear that, Larry. I've never had any of these types of scans done to me. So, but yeah, if someone here has any sort of like, medical background, maybe you guys can learn to talk again, which I'm happy to hear. But if someone has a medical background here, maybe you guys can, just chime in a little bit here on that particular question. And what sort of information you can probably get from out of the two. Because that particular information I have no idea about. All right. So, earlier I stated I wanted to make up a problem on this. And so let me go back. So right now you guys can see the internet. Okay. Here's our problem. I read online that MRI machines are basically pulsing RF signals, so radio frequency signals. One particular radio frequency that I know of is the 21 centimeter line. I know that's a radio frequency. So we're going to assume this, or here's our scenario. Our MRI machine only has the capability of pulsing the 21 centimeter line frequency into our patient. Let's determine, of course, what sort of magnetic field will we need to generate. That is, in this case, B sub t. And let me switch so you guys can see the equation as well. What sort of field will we have to generate in order for us to even produce an image? Remember that the MRI is not only controlling the field that's going into our target or our patient, but it's also controlling the light that's also hitting our target. So it's controlling both B sub t and it's controlling nu, or the frequency. So in this situation, we just need to be able to, of course, solve for B sub t, given that we know what nu is. And then we can start making some other comparisons once we figure out that external field strength. All right, so I'm going to modify the equation. So we're going to solve for the field strength. Given that our frequency is going to be 21 centimeters. And so in this situation, when using any sort of equation, you need to make sure that your units are going to be good. So I'm most comfortable working with SI units. So 21 centimeters, and of course centimeters is not the SI unit, meters is. It's going to be equivalent to 0.21 meters. All right. So far, so good. Our new equation we should end up getting is going to be B sub t is equal to, oops, undo that. Put that there. And this is going to end up being h nu divided by 2 times the magnetic moment of a proton. And I'm realizing now that that we need to also know what the magnetic moment of a proton is. And so, okay, yeah, we could just go with this. And so, actually, let's quickly find that information because we need it to solve this problem. The 21 centimeter line, like the yes. So 21 centimeters corresponds to the radiation from neutral hydrogen, so H1. And if I'm not mistaken, and you guys verify this, but I think it's a forbidden transition. I think it's one of those forbidden transitions, actually. So yeah, good thing we brought this up, actually. So the same effect, the fact that the external field splits the when you have a proton in the presence of an external field, and it splits into being in this spin up and spin down state difference in energy levels. The same effect actually happens to atoms and electrons, right? If you have a what's up, Michael T. Mayer? Welcome. Did I? Oh, thank you for making that correction. I would have done the problem. So what Michael is saying here is that 21 centimeters is a wavelength, and my equation is in terms of frequency. So I have to make the proper conversion, of course, in my equation to account for a wavelength, or convert the wavelength to a frequency. But in this case, the correction would have to be, instead of nu, because the speed of light is equal to the wavelength times the frequency. This is now going to become you're right. It's going to be h. Isn't it going to be c over nu? So it's 2 times nu. I think this is the correction. Good catch there, man, guys. See, this is the reason why you guys have to watch me. Make sure I'm doing this correct. And this shouldn't be nu. It should be lambda. Okay, I think that this is one. It's going to be it's unit wise it's correct, but it's also going to be correct for and given a wavelength. All right, there we go. We're good to go. So, and also just in case someone's like looking at this later and wondering where did that come from, up here I'm going to put c over lambda. Okay, I think we're good to go now, guys. And again, guys, thank you for catching that. Oh man. I would have been like, later I would have been like, what's going on here? It's not working. But all right. So we're good with this. So now what we're going to do is, I was answering some quick questions here. Hello, Missy0106. Welcome to today's stream. And I only followed D times. What's going on? So basically what we're doing here is we're talking about MRIs and more so the physics behind them and how they work. And so what we basically solve for here is the fact that whenever we have our patient going into the MRI machine, the MRI machine produces these static magnetic fields. That is, magnetic fields that are oriented in a specific way that pass through our patient. What ends up happening within the patient, for example, with the free protons within the patient, those protons then undergo a specific alignment. And those alignments will either be what's considered to be spin up or spin down. Well, given those two different alignments, there's going to be an energy difference in those two states. And so what we solved for here was that the energy difference is going to be related to, one, the magnetic field that the MRI is producing that's passing through our patient, and two, the radio frequency pulses that the MRI is also dumping into. Well, yeah, the change of energy is equal to both of those things. But basically, you basically get an equation that equates the two. That is the field strength that's passing through our patient. It's going to be equal to Planck's constant times the speed of light divided by 2 times the wavelength of the light that the MRI machine's also dumping into our patient times the in this case the magnetic moment of a proton, because we're only considering this effect to occur on the free protons. I hope that I quickly explained that really and well, because 10 minutes is left. I want to be able to get through this part of it. But if you have any other questions, by all means, just keep this shooting my way. All right. So, what we want to do now is, given the 21 centimeter line, we want to be able to find out what the corresponding field would have to be in order for us to get an image. Or a higher resolution image, actually. I guess the protons that are already in a spin down state could undergo de-excitation, but well, wait a second. Wait, let me rephrase that actually, now that I think about it. While in the presence of the field, though, the protons that are already in an excited state, I would assume would probably remain there, maybe? And would remain there until, I guess, we remove the external field. I'm not too sure, actually. I gotta think about that. I think actually the field would probably still have to be present, because without the field, you don't get these two states. Okay. So let's go ahead and solve for what the field would have to be, given that we are pumping a radio frequency of 21 centimeters. And I was stating something earlier about this, and I think it was related to the Zeeman effect of how neutral hydrogen I might come back to that later, actually. Right. So yeah, I was going to talk about the fact of the Zeeman effect, and I think that's what's occurring with how the 21 centimeter line is produced. And the Zeeman effect specifically occurs for electron energy levels, whereas this particular effect we're talking about is occurring with the proton itself within the nucleus, having two different states. Right, let me quickly do this though. So we got 0.21 meters, and we're going to go ahead and solve for this. And we actually need one more bit of information, actually. We need to know what the magnetic moment of a proton is. So let's go back to scene 1. And let's go ahead and type in magnetic moment of proton. I think it's called that. And this is the value that we want to use. Or no, that's not right. It has an extra factor of mu sub n. Let's use this value, which is in units of, it's in SI units. So I'm actually just going to kind of copy and paste this. And just in case you guys are wondering what the magnetic moment is, if you have a proton, it will of course have its own intrinsic spin. If you place it into an external field, what happens is that field will cause a torque on the proton. And this is measuring, I guess, the amount of that torque, if I'm not mistaken. Yes, I see the word torque in here somewhere, but I don't know if I'm explaining that. I think I'm explaining that correctly, though. It causes a torque on the proton. But let's quickly get through this, though. And if that's wrong, guys, let me know, of course. But let's continue. So, going back here, I'm also going to put in parentheses that, let's say, that mu sub p is going to be equal to that number. All right. Just making a few formatting changes here. All right. I think that this should be good. All right. So now we can go ahead and solve for what that field strength should be. So have our fraction. Times like this, I wish that I could have just set up a function within like a C program and have it do the math for me. Up top for h, Planck's constant, which I know it's like 6 times 10 to the negative 30 something, 34 probably, on that side, but I want to make sure of that. Let's go back. Well, first off, let me send you guys here so you can see what I was doing there. And I'm just going to quickly go back and figure out what that constant is. And at some point, I know I'm going to have to go check the comments because I'm pretty sure I've like missed out on stuff. Let's do that now, actually. Yeah, you're right, Larry. Is that correct, guys? Because I'm vaguely remembering that the 21 centimeter line is it happens occasionally, right? But the thing about it is that there's so much hydrogen content within our universe that, you know, that's the reason why it happens, you know, pretty often. If we didn't have so much hydrogen content, it would happen rarely. It would rarely happen. But can someone verify, is the reason why it does this because of the Zeeman effect? Does it say that within the wiki? All right, let me continue with this. So back to tech, and you guys should be able to see the tech stuff. All right. So H is going to be this long number. And for right now, let's keep the units because I want to make sure I'm keeping track of things. Let's see if this typesets. That works. C is going to be, I kind of remember C, so 3 times 10 raised to the 8th power in units of meters per second. Let's just put the per second. And then we have, in our denominator, we're going to have lambda, which is 0.2 meters, or 0.21 meters. 2.1 times 10 raised to the -1 power. And lastly, we have our magnetic moment value. Get rid of that 97 times 10 raised to the -26. JT raised to the -1 power. I think this is good. Or here we go. Okay, and so our final unit, of course, is going to be the Tesla, which is the SI unit for magnetic field strength. And so what we end up getting, and I'm going to try to quickly type this into my calculator. And it's an SI unit, so this is actually pretty good. So I'll just do 6.626 times 3 divided by the quantity 2 times 2.1 times 1.41. And I think I got, and that comes up to be a very nice number to deal with, actually. So roughly 3.34. And this is going to be times, wait. All right, so that's it, the Zeeman effect. Oh, I'm sorry. I'm sorry if that bothered you. But yeah, the Zeeman effect is a pretty important effect. And now to deal with the powers of 10. That's a little bit easier. So -34, 8 makes -26. -25, right? Is that right? Oh wait, -26. The -26 from that other constant for the magnetic moment, those cancel out, and so you basically just get a power of 10. So it's 33.4. It's kind of what I'm getting here. And I can get rid of that times. It's going to be Tesla. So 33.4 Tesla would be the magnetic field that needs to be produced by the MRI machine if you are pulsing a radio frequency of 21 centimeters. I mean, pulsing a wavelength of 21 centimeters into your patient in order for you to produce images. Or high resolution images, I guess that's a better way of putting it. Oh man! So does anyone here have a medical background, and know any of this stuff with MRIs and stuff like that? And also, Michael, you always save the day with the math. If I'm doing something wrong here, let me know. With the math, that is, because I miss little things like that at times, and it's not until later when I'm looking at it oh wait, that's not right what I just said there. But yeah, this is one of those problems that generated right before the session and right before the stream, and I thought it would be something interesting to talk about. Okay, I'm happy to hear that. Cool, Uncle Bill Druin. Yeah, definitely keep me honest here, guys. If you guys catch something that's not right, let me know, because I need to make those corrections. Yes, I'm happy to hear that you made the whole hour, Larry. I'm happy that I didn't do anything to, you know, make the experience bad or anything. Well, I don't know if you guys have any questions about, what we discussed here. If you do, by all means, go ahead and throw them my way. From my understanding, I mean, you can use this the MRI technique to do a lot of cool stuff actually. Because you have to take into consideration how you want to be able to produce your images, whether they're going to be 2D or 3D. And when you're doing 3D images, there's other things you have to be, concerned about. So, but yeah, now I'm actually quite interested in like making sure what I said earlier about the 21 centimeter line was correct. 21 centimeter line. Let's see if it just gives me. Because it might not be due to the Zeeman effect. So now I'm going to take that back what I said earlier. So the 21 centimeter line is not caused by the Zeeman effect. So by all means, please disregard that statement. So let's see. So I just looked at an article on MRI. It said that the frequency is typically 64 megahertz. All right. With a field of about 1.5 Tesla. So the interesting thing about it was I was reading online was that these field strengths, as far as like the human body is concerned, is not. It's not like a. It's not like it would be harmful. Even on the order of like tens of Tesla. But you know what? This is actually a good way of being able to check what I've done here. Right? If we look at the equation, so let's go back to that equation. Yeah, in this situation, the 21 centimeter line is being produced by electrons within hydrogen atoms when they de-excite. The only reason why thought of using it was because of that fact that I know. So I wanted to use it with the whole MRI problem. But I'm going to use what Michael Mayer just said there about the fact that given that frequency, we get that field. And so given what we know now about the relationship between field and frequency, I would say that they're directly proportional to one another. In other words, if you increase one, you're going to increase the other. Yeah, microwave. That's right. The 21 centimeter line is the microwave. And microwaves are just like high energy radio waves. Mm-hmm. It's our primary means of being able to study neutral hydrogen content within galaxies. But I had a plan here. I wanted to do the conversion. I'm just going to go online and do this really fast, actually. And then I'm probably going to end the stream after this. So I could do it myself, but I'm just going to allow the internet to tell me. Let's do frequency or wavelength to frequency. And of course, we're talking about light here because the relationship, the equation for the relationship is the same for other types of waves like sound waves. But in the case of light, the speed is always going to be c. Okay, so perfect. We want to do a wavelength of 21 centimeters. This corresponds to 1,000. So this is 1.4 gigahertz roughly. All right. So I'm going to go ahead and go back to what Michael stated earlier. So Michael stated at 64 megahertz, we get 1.5 Tesla. So if I multiply 1.5 Tesla times, what's the division here? 33? Is that what we end up getting? Let's see. Go back to our problem. I wanted to do this. And so we end up getting 33.4 Tesla. So we're going to take 33.4 Tesla and divide it by, what was that? 1.5 Tesla. That's a factor of only 20. So, whoa. That's a factor of 22. So I need to be concerned here now. 22. Or do I? 22, 64. Yeah, something's... .21 centimeters gives one. That's a factor of megahertz. That's 1427 divided by, what was that? 64? Oh, no, never mind. It's good. It's good. All right. I was worried there for a second. So yeah, the math comes up to be about roughly right. So we're good. So what I was trying to do was verify if my answer is correct. So the idea here is that the ratio between our answer to 1.5 should equal to the ratio, or the ratio of our answer for the magnetic field divided by the 1.5 Tesla that Michael stated. That ratio should be equal to the ratio between our answer for the frequency, or the frequency we use in our problem, relative to 64 megahertz, and it is. So I was just checking our answer, that's all. And everything looks like it worked out. So microwave ovens run at about 2.4 megahertz. So if that's the case, I mean, what would really be interesting exactly how can we put that into physical sense though, the field strength. I wonder how strong are like kitchen magnets, you know, like on the refrigerator. Let's do this. I'm curious about that now. Let's see. How strong are kitchen magnets? Oh, this is gonna go into like. I just want to know how strong a kitchen magnet is. All right. I'm not seeing any like immediate numbers pop up somewhere to make a comparison, or maybe even compare it to the Earth's magnetic field or something like that. But strong enough. Oh, that's a fun problem, right? That would be a fun little problem, right? We could we can actually figure that out, right? We'd have to balance. At the very least we can get a minimum, right? We can balance the gravitational force of a magnet to its the magnetic force it has. Oh, is that what you're saying for the 21 centimeter? The Is that what you're saying for the MRI? For us to be able to produce, yeah, I think I would have to agree with you on that, Michael. For us to be able to produce a MRI that's able to produce 1.4 thousand, what was that? Was that or 33.4 Tesla field? We need a really a relatively big setup. Yeah. I wonder what sort of field strengths they use at like the what is that? At CERN. Ferromagnetic. I'm trying to remember what that is. There's the P one. There's the I'm sorry, Larry. My it's been a while since I've talked about stuff like that. Ferromagnetic versus the other one. It's 100 Gauss, so we'd have to convert that because I don't think Gauss isn't Gauss is not just simply magnetic field, is it? Is it like field per unit area? Can you guys see what I'm typing here? Let's make sure, yeah. Gauss. I think it's field per unit area, so we'd have to. Yeah, it's okay. Yeah, the Gauss is a field per unit area, right? No, it's not. It's field. I'm wrong. It's just simply field, but it's in a different. It's a different kind of unit. Okay, because it's equal to 10 to the negative 4 Tesla. All right. It's actually just strictly field. Yeah, guys, as we talk more and more about this, you're going to see some of the things that I've kind of forgotten here. I don't think about these things on a daily basis. But it's definitely fun to kind of like recall some of it. Yeah, ferro means iron. So yeah, there's like yeah, and yeah, there's ferromagnetic, and then there's the other one, right? I think it starts with a P. Para or paramagnetic? Is that it? Let's see. Yeah, ferromagnetic and paramagnetic. All right, guys. I've definitely had a great time talking to you guys about this. Okay, those are the other ones. Are paramagnetic and diamagnetic. Cool. Well, guys, thank you guys for like stopping by. Had a great time. Thank you, Missy. You're a new person here. Welcome. But well, guys, thank you guys for stopping by. Had a great time talking about this stuff. Um, by all means, send me stuff on, if you have access, that is, on the weekly Space Hangout Cruise Slack, and hopefully one day I can make it a topic. All right, guys, that's it for me for today. I'll be back on next Wednesday at 12 p.m. Central, and see you guys later. Thanks, guys. Bye, all. Bye, Missy. See you, Tom Van Scotter. Thanks. See you, Skeptic Psy. No problem, Guido. All right, I'll see you guys later.